period of a pendulum can be calculated with the following equation. Using the small angle approximation, our equation can be simplified. Our new equation allows for much easier calculations, where t is the period and is dependent on L, the length, and g, gravity. We have conducted 5 experiments in order to confirm the equation. Our first experiment shows that the mass has no effect on the pendulum's period. The following clip is a side-by-side comparison of 2 pendulums with different masses. As you can see, the pendulums share the same period. Next, we will prove that the period is dependent on L to the 1/2 power. It is apparent that the shorter stringed pendulum's periods were much shorter than the long stringed pendulums. The timers used in the editing software follow the time code, so our units are not seconds. Let's look at the actual data we obtained to prove the period depends on L to the 1/2 power. Here is our simplified equation again. First, let's solve for L to the 1/2. Then we'll replace the 1/2 with the variable x. Next, we'll isolate x, plug in our data, and have our x. Ignoring units because they will cancel, the x we obtain is 0.53, which is pretty close to 1/2. Our next task involves proving g equals 9.8 meters per second squared. Using the data from the previous experiments, we can solve for g. Referring back to our simplified equation and solving for g gives us the following. Now plugging in the data we obtained from our experiments gives g equals 10 meters per second squared. Next, we'll show that our equation is only valid for small angles. This is because we use the small angle approximation to simplify the first equation presented at the beginning of the video. This next clip shows the error of a large angle. Also, momentum is lost due to energy being transferred out of the system. This graph shows the percent of error of our equation. As our angle theta increases, so does our percent error. Our final task was finding the cause of the small error within our data. A small amount of momentum is lost due to friction and air resistance. There are many possibilities of human error, including not dropping the mass correctly and discrepancies in the exact spot a period is completed. Also, any angle above a few degrees will begin to have an error due to using the small angle approximation. And our pendulum is not a perfect system, but the equation assumes it is. The weight is not a point mass, and the string itself has mass too. The period of the pendulum is unaffected by its weight, but the period is affected by its length to the 1/2 power. Proven by our data, gravity equals 9.8 meters per second squared. Minimizing the size of the pendulum's angle and minimizing any human interference will greatly reduce any error.